Okay, and welcome back. So I'm going to talk to you about the limit of a function, and we'll start with the definition. Okay, and the definition states, let f be a function that is defined at every number in some open interval containing a. Well, here's a function, f of x, and here's the open interval containing a. Okay, so let f be a function that is defined at every number in some open interval containing a. Well, what it means to be defined at every number means that every single x I plug into here, there's a number that corresponds to it on this curve here, on the y-axis, basically. So that means it's defined. If a number is defined, that means there's a point on the graph that corresponds to it. Okay, and now it says except possibly a itself. Let me put this into perspective in a real life situation. Let's say, for instance, well, let's get rid of these little blue marks here. Let's imagine, for instance, that you are walking along this path here, okay, and you're going in this direction here, and you're going in this direction here. Either way, it doesn't matter. You're coming in from this side or from this side, meaning you're plugging in values going close to a on this side and going close to a on this side. Which means that on the left, if you're getting closer this way, that means you're going to get values that go up this way, right? So maybe I should do that in a different color. So let's say you have numbers you're plugging in numbers going in this direction. They'll correspond to numbers on the y-axis going there. And then in blue here, you have numbers going closer and closer to this a, which means that you'll have numbers getting closer and closer to a particular point on this y-axis, and that point over here is this one right here. That's the limit. Okay, the limit of the function when it gets to a certain number is some type of value on the y-axis. Okay, so in this case here, if this had been some kind of function where you're plugging in the a into it, it's gonna spit out this L here. So if this had been x squared, if this had been 2, you plug the 2 into the x squared, it's going to give you a 4, and then the 4 would be over here. Okay. Now, when they say except possibly a itself, what it means is, let's say you had a function that had a hole in it. Well, in a real life situation, let's go back to this where you're just walking on the path here. In a real life situation, it basically means that you're plugging in numbers, and they're valid on this curve right here. You're plugging in numbers from the x-axis into the function, and you're getting points along this curve over here. So as you're walking in this direction, going in this direction, you're going to go to your friend's house, right? And so you'll end up at this destination, which is the limit of your destination. When they say except possibly a itself, it basically means that maybe he's just not home at the time. That's where you have like a hole in the graph. And that's it. But the limit still exists. Remember, the limit still exists even if there's nothing at that point. Meaning if the point is empty. Meaning you can't plug something into your function. Okay, so an example, which we'll work out later on, would be this one here. X minus 2 over x squared minus 4 as x approaches 2. Here the limit does exist, even though it looks like it doesn't, because you have, you plug in a 2 on the top, you get a 0, and 0 is not the limit. And if you plug a 2 in the bottom here, you get undefined, so undefined is not the answer either. As a matter of fact, the limit actually does exist, believe it or not. You'll use different techniques for finding the limit. In this one here, you'll have to factor out. But for right now, let's worry about the concept of the limit, in the sense that what you're doing is you're plugging in numbers into a function, and they're approaching closer and closer to a particular number on the y-axis. So this definition holds if the following statement is true. For all epsilon greater than 0, there exists a delta greater than 0. Let me stop right there. I'm sure some of you are like, what does that mean? First of all, I'm going to make this very basic. This is not the core of this tutorial, and this is more theory based, so we're not going to be talking about a lot of theory here. We're just going to be working on the concept. But for right now, Let me just kind of explain quickly what this means. With this right here, just starting this off, I have to explain what this little mini e is. Well, first of all, this upside down a, it means all, or for all. This backwards e means for every. Okay, and this is a universal quantifier. This is an existential quantifier. This little mini e here stands for epsilon, and this little d here stands for delta. These are Greek symbols. Anyway, it's basically saying for all epsilon greater than 0, meaning for all positive values of epsilon. Epsilon is the distance between here and right about the L and right below it, right above it and right below it. Now, how do you determine what's right above it? Well, if you draw a little line over here, it looks like it goes right above the point you were at, right? It's like right around here. And right below it would be somewhere right about here. Well, if you have a gap right here between the actual limit of your function on the top and on the bottom, these correspond to some type of number, and this distance between right here and this one over here, the distance between this x and the a basically means this x and this a, this x and this a. The difference in between here, this is called a delta tolerance. This over here is called an epsilon tolerance. It's the gaps between the value of this x in the function corresponding to a value on the y-axis and the limit itself, both on the top and the bottom. You may have to rewind this to understand what I just said, but basically what it means is if I plug in this number x, this x, into the function, it's pretty close to the a, but if I plug in this number, it's going to give me a point on this graph that corresponds to a value on the y-axis right about here, and the distance between this number on the y-axis and the L, the limit basically, that little gap in there, that's my epsilon. So that means for all epsilon, in any situation, if you have a little gap, there exists a delta. It basically means that there's a gap over here. That's what that means. For all these little gaps on the y-axis, that's what this means. There exists a little gap on the x-axis. And such that, and then this kind of just breaks it down a little bit more, the implication, meaning that this delta right here, which is basically what this means, this whole thing right here means that if you subtract this x and this a, you're going to get a delta. As long as that delta is greater than 0 and less than maybe a specified one that they give to you. Again, this is theory, don't worry about it too much. You could even skip ahead really, but this is just theory that sometimes, depends on what teacher you have, depends on what professor you have. They may go more into theory, depends on what their background is. But anyway, what I was saying was that if there's a gap over here, then it implies that there's going to be a gap over here. It's kind of like really this right here, a gap here implies that there's a gap over here. That's what this arrow is for right here. It implies that the function minus the limit is less than epsilon. Basically it just means that this function value over here minus this epsilon minus this limit over here, so the function value you get, whatever it is, maybe this, by plugging in this number into here, that function value minus the limit itself should be a little bit less than maybe an epsilon that they gave to you. Again, let's not worry about that too much, but sometimes you'll be given one or the other. And then this is kind of what makes calculus difficult, is this topic right here. But right now, let's go back to walking on the curve. Remember, all we need to do is understand you're basically going on one side of the curve and on the other side of the curve, and you're reaching a point. Maybe your friend's home, maybe he's not. That's all we need to worry about. All this right here, I hope you appreciate some of it, but it's not necessary for what we're talking about right now. Anyway, now the way to write the limit of a function is like this. The limit of f of x as x approaches a is L. And to help you remember how to say it, there's a little mnemonic device that I use. It's the limit of f of x as x approaches a is L. It looks like the number 2. So that's how you can remember to say it. And this is the way to say it right here. So like, I'll give you an example. The limit of x squared as x approaches 2 is 4. You see? Or the limit of x cubed as x approaches 2 is 8. Easy, right? Okay, so now let's do some examples here. And the first example is going to be a simple one. So some of you guys might roll your eyes on this, but you know what? It's necessary to kind of ease into this. You know, I don't want to make things too difficult. It's already bad enough, some of the explanations that you get from professors. Sometimes they don't realize what they're doing, but they may throw something from later topics into, because they're excited to show you this stuff. You know, I mean, it's great. This is beautiful information. They're excited to show you, you know, what's to come. So sometimes they get carried away and they may throw in extra things, and you're like, well, how does that relate to what you just said 30 seconds ago? And that typically happens in calculus classes. But in this one here, I know I'm throwing a lot of stuff out at you. Just watch this video again if you need to. Skip things that you find that are, you know, that I tell you they're okay to skip. Like, you could totally skip that whole, you can skip all this part over here. Anything that had to do with this right here, you could very well just skip it. It's just this part over here and walking on the curve. That was, oh, one more thing I want to mention. I'm going to say this one time, but you'll remember me when you get to it. When you get to a topic called continuity, I want you to think of this. Think of this going this way and going this way, and you're talking about that particular place. Just remember this T. It looks like a giant T, right? So this thing's continuous if you're going from this side and this side, they match up, and if there's something over here, basically. Just remember that. I'm only going to say that once, and that was it. I don't want to start going into a different topic. I just want to say that. Just remember that T formation. You see, it's kind of important. Trust me, later on you'll understand it. You'll understand what I'm talking about. But I think I should mention that now. Somehow I feel that the way I remember it is like that. And I think if I was told that from the beginning, I think it would have made stuff that I saw later on, which you guys are going to see, it makes it a little bit more understandable. Anyway, just let that sink in. Just remember that. Going in from this side and going in from that side, and you're talking about what's inside of there. Okay? Now, the examples. So first one is, what is the limit of x squared plus 1 as x approaches 3? Well, that's easy. You just plug in a 3 into your function, and you get 3 squared 9, 1, 10. Right? That's easy. All right, how about this one here? The limit of sine of x over 2 as x approaches pi. Well, let's plug that in. Sine pi over 2 is equal to what? Well, that's 1. If you're familiar with your trig table or you just memorize it, it's 1. Okay? So notice how these, and now I'm choosing these specific functions because I know that there's no like jump. It doesn't do something like this and then it jumps over here to somewhere else. They're all either nice little curves or a straight line or a parabola. I'm only giving you things like that right now for these examples here. So, you know, I am showing you stuff that's kind of easy. Again, if some of you guys are rolling your eyes on this thing, that's fine. You know, but some students out there that will appreciate, you know, kind of easing into this thing. So just kind of bear with me. I promise you, they're going to get more difficult. Okay, so let's do that example I was talking about earlier. The limit of x minus 2 over x squared minus 4 as x approaches 2. Well, you see, you can't really plug the number 2 into here because it becomes undefined on the bottom. That's the first thing you should do is, can you plug the number into the bottom? Don't worry about the top. This top could be 0, it can be anything you want. It's really the bottom. If it's undefined, you gotta try to see if you are able to maybe factor. You could try factoring. You can try the conjugate, but not in this situation. This situation here, it's easy. It's factoring. But we'll do a conjugate problem later. But I'll show you guys how to write this out, because there's 2 things I'm showing you in this example. 1, the notation, and 2, basically a technique. So the lim of x minus 2 over, the bottom is a difference of squares. Okay, so you've got x plus 2, x minus 2 as x approaches 2, and this cancels with that. And so you're left with the limit of 1 over x plus 2 as x approaches 2. And so now you could just plug the 2 into it. Okay? And that's equal to 1/4. Notice how I wrote the lim here. I wrote the lim here. And I dropped it over here. Okay? It just kind of like it disappeared. Writing the lim is kind of writing the lim on algebraic manipulation is kind of like writing capitalizing the first letter of every sentence. It's just the right thing to do. It's the proper way of writing this out. So you can only drop the lim when you're plugging numbers in, okay, or evaluating the function. That's basically it. That's it. I mean, plugging numbers in is evaluating the function at that value. So you are only able to do it once you get to this point. So 2 things to remember. You know, keep the lim all the time until you finally get to something that you can plug numbers in. Then the other thing is you can drop the lim when you're just doing computations. Okay. So lim gets dropped on computations, but you keep the lim when you're just doing nothing but the algebra involved before you plug something in. Okay, so in this case here, this one here, you had to use factoring in order to be able to get an answer. All right, so now let's go to the next example. So in this case here, if you plug in the 25, you're going to get a 0 on the bottom. Again, I'm looking at the bottom. I'm not really worried too much about the top. Now, if this had been x approaching negative 25, well, then you'd have a problem with the top because you can't have a negative number. But for right now, they're going to be really simple like this. It's just going to be something where the denominators usually end up zeroing out. I mean, for the most part, that's how just about every single question is going to be phrased. Your professor or teacher is going to make the denominator 0, and then you just have to do something. The last example we factored. This one here, remember in pre-calculus and in algebra, something called multiplying by the conjugate. You guys remember conjugates? Well, this is what it was for. So you're going to multiply by the conjugate. The conjugate here, you're going to rationalize the numerator. Okay? By rationalizing the numerator, allows you to be able to get rid of your radical on the top, but at the same time, it's going to give you a result that will end up factoring out something in the bottom. So here we're going to write the lim again. Again, you know, I'm just doing an algebraic operation, so I'm keeping the lim. So I've got x minus 5 times rad x minus 5 plus 5, and on the bottom, x minus 25 and rad x plus 5. So the conjugate of rad x minus 5 is rad x plus 5. So top and the bottom, multiply that, top and the bottom. Now, as x approaches 25. Now on the top, again, I'm writing the lim because I'm just doing another algebraic. I'm not plugging in anything, so I write the lim. Okay? So the top is of the form a minus b times a plus b. So the result is a squared minus b squared. So it's going to be x minus 25. Now, on the bottom, I'm not going to FOIL this out, okay? I'm not going to go through it, but if you FOIL it out and you try to plug the 25 into it, first of all, nothing's going to cancel out, and secondly, it's going to come out to be 0 anyway on the bottom because you're just really multiplying you're using the multiplicative identity of 1 on this function. Basically, you're multiplying by 1. The conjugate is just a 1. That's basically what it is. So it doesn't mean anything's going to change. It just means the bottom is going to remain 0. So what you want to do is, using this technique here of using conjugates, multiply by the conjugate, it eliminates factors at times, and this is one of them right here. So you're going to have x minus 25 and radical x plus 5 as x approaches 25. Now this cancels with this. Now, I'm going to stop here because this is something that you will probably never hear from anybody else at this level and maybe this early in a calculus class. One thing you should always remember is don't be so quick to FOIL things out. Just trust me on that. You'll remember this when you're doing differentiation. You'll remember this when you're doing integration. That things work out a lot better sometimes when you don't FOIL things out or distribute things out. As a matter of fact, try to avoid it at all times. Try to avoid it whatsoever. Now, you'll remember me when you get to a problem and you're stuck. You're just sweating it out going, what is going on here? And you're just manipulating stuff algebraically. Remember, once you get stuck, remember me. Go back. This is me talking to you. Start over again. But this time, whatever it is you're doing, at the point that you distributed something, don't distribute. Now, don't erase the work you did. Just go back and don't distribute and just keep everything in factored form. In this case here, now look how nice it's going to work out. I'll put it on the next line because it looks like I'm running out of space. I like having plenty of space. Limit, and that's a 1 at the top basically. It's 1 over rad x plus 5 as x approaches 25. Okay, so you plug then 25 into here and you're going to get 1 over radical 25 plus 5. And so that's 1 over 5 plus 5, and that's equal to 1/10. Now notice, you see, now I can drop my lim because I'm plugging numbers in, and it's just nothing but computations. Okay? I'm going to go back again to this whole canceling deal. You see, this is another thing too. You know, I'm really glad that you guys are hearing this because, man, these are things that you would never get until it was too late. Seriously. Like, I don't even know why it's not even in the books, but they should really tell you. Try not to FOIL things out. Try not to distribute. Just leave things in factored form. You will be so happy when you get to, especially when you get to integration, because that's kind of like the breaking point for a lot of people. They have a hard time with that. That's probably one of the more difficult topics in calculus is that. And it's because they keep distributing. Students keep distributing, or you'll get stuck and you think you did something wrong. You didn't do anything wrong. As a matter of fact, if you were to evaluate whatever it is you're working on, your answer still would be the same. That means if you were using a pretty advanced calculator and plugging in whatever it is you were, whatever number you were looking at, I guess, whatever number you were dealing with, and checking the result every step along the way, your answer would come out to probably be right. The problem is, though, when during the manipulation you're trying to make it look like something else and it's just not working out, it's because you probably factored something and you distributed, and that distribution right there kind of just made a mess of stuff. So, because if you look at this right here, look at this. X times rad x, you get x rad x. And then you'd have 5 times x plus 5x. Anyway, you'd be canceling things out and things would work out, and you'd plug in your 25 at the very end and you still get 0 at the bottom. But this way here you don't. So it's a very powerful technique, and again, you notice how much I'm stressing on it. You know, the clue should be, wow, this must be pretty significant. Why would he waste his time talking about it so much? So anyway, let's move on. Okay, so the last example I want to do on here before I move on to the next piece of the puzzle is this function here. I didn't want to make this complicated. I just want to make this simple because it's once you get the idea, then you can do more difficult problems. But basically it's 1 over x. Notice on all these other ones it looks like you're getting a result, you see? But the problem is with this one here is x approaches 0, there is no Well, first of all, there's no limit. I can tell you this one, I'm just going to tell you what the answer is. Does not exist, okay? The answer is does not exist. And I'll explain why. In this particular function, the graph as you know it looks something like this, and it goes from here to here, like that. Now, you see it's an odd power on the bottom. If it was 1 over x, 1 over x cubed, 1 over x to the fifth, it just gets tighter and tighter in here, but still, you still pass through 1, 1. But the problem is that it makes this swoop effect where you're going swoop this way and swoop that way. So it looks like it's going in two completely different directions. So if the car was traveling this, or you were walking this way and you were walking this way, does it look like you're going to the same place? Nope, you're going in two different directions. That means it does not exist. Even though there's nothing in the middle right here at 0, there's no value for it, but still it means, but you're going in two different directions. Now, the reason I'm mentioning that is because that brings me up to the next topic. And the next topic is the one-sided limits, okay? Because from one side I'm going one way, and from this side I'm going to the other, okay? So let me bring that up. Okay, and so here's the definition for one-sided limits. Let's just make this a lot easier on yourselves. Let's just look at this graph here. Let f be a function that is defined at every number in an open interval, a to c. Okay, a to c. All right, and then the limit of f of x is as x approaches a from the right. So basically, c is just like 1 to 3. So the x's are the ones inside of here. As you're going in this direction, you know, it looks like it's approaching that point right there. It's like the other graph, except the open interval is shifted to the right of that point you were dealing with, and you're talking about stuff happening on this side. So now we're being specific, and we're just talking about things that are occurring on the right-hand side. Now for the left-hand side, that's a. Here's another c over here. Then let f be a function, blah, 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 in the open interval c to a. So basically it just means from c to a, and then the limit of f of x as x approaches a from the left is L. So there it is. You see, that's now you're just being really specific. And the way to write it is like this. When you're coming in from the right, it's little positive. It means coming from the right because the right is positive, right? So the limit of, that's the only thing that changes. Normally it would just be x approaching a, but here it's a from the right, from the plus sign side. And then here the left would be from the left side, the minus side. So a plus, a from the right is plus, a to the left is minus, okay? A from the right is plus, a from the left is minus. Okay, so as far as the epsilon delta notation for the definition of a one-sided limit, what I'm going to do is, to save time, I'm going to go back to the original definition I showed you guys before. Okay, sorry to cram everything in here, but basically this is what it is. This would be the definition, just like the original. The only difference is this. I'm going to show you guys what the main change would be. It's the absolute value bars. They're not there. And when you are talking about the limit from the right, this would be x minus a. And when it's coming from the left, it's going to be a minus x. Okay. And that's the only change. Okay, so now let's work with some examples. All right, notice this graph here. This function itself is composed of two subfunctions in this piecewise function. And the function x squared plus 1 is over here. And this function 2x minus 2 is over here. And if and this function is valid if x is greater than or equal to 3. Okay? So now let's look at this. Oh, well, and this one here. And this function here is valid 2x minus 2 if x is less than 3. Here. Okay. So let's take a look at the limit of the function f of x as x approaches 3 from the left. So as x approaches 3 from the left, you're riding along this way here, and it looks like it's going to 4, right? So let's check that. As a matter of fact, I'll use a different color. So x coming from the left, well, that means this over here. Now, if we didn't have the graph, we would just look at this and say, well, coming from the left, they're talking about 3. So we're looking at things less than 3 from the left, and here it is, less than 3. So it's going to be limit of 2x minus 2 as x approaches 3 from the left is equal to, well, we can plug that in. You're going to plug in the 3 into the 2x minus 2. So it's going to be 2 times 3 minus 2. And that's equal to 6 minus 2 is 4. So notice here I don't have a lim because I'm just plugging in numbers. And then here, the lim, or the limit of f of x as x approaches 3 from the right. So without looking at the graph, from the right would be numbers greater than 3. Here's x greater than or equal to 3, and so that's x squared plus 1. So it's the limit of x squared plus 1 as x approaches 3 from the right is equal to, well, let's plug that in. You have 3 squared. Notice I'm dropping the lim now. 3 squared plus 1, and that's equal to 10. So now, remember a little while ago, well, remember earlier, that the problems kind of pose themselves like this. There's no sign plus or minus here. It was just a number, like x approaching a number. See, now this has a little bit more substance to it before you can answer it. The only way you can answer this properly, okay, really in this case here, the way the question now is asking, what is the limit of the function? Well, before we knew that they were coming in from both sides. It was just a nice function. But this one here is a piecewise function. And in some cases, the functions are kind of strange where you have things, that run off to infinity. But that's a different story, altogether a different topic. But in this case here, the way to answer this is on the left and to the right of 3. Does it look like it's approaching the same number? Well, I'm walking this way and I'm walking that way. But look, it doesn't really connect. I can't really make my T formation, right? There's no real T. It's not even possible. Okay, so to answer this question now, you have to ask yourself, well, does the limit of this and does the limit of this equal the same thing? Okay? And the answer is no. So in this case here, the limit does not exist. See, while this one's going to 4, this one's going off to 10. These are completely different places. They don't go to the same spot. There's a big jump in here. Okay? So this would be an example of a limit that does not exist. But you found the limit from going from the left and from the right. You notice that, you see? You're going from, well, in this case here, the top one is the one coming from the right. And the bottom one here is the one coming from the left. Okay, so coming from the left is this one here. Coming from the right is the one up on the top. Okay, so that's that example. So this time what we have is a piecewise function, but we're not going to sketch out the graph this time. Now we're going to do this thing analytically. So let's take a look at this. Does the limit of f of x exist? Well, first of all, if it exists, you have to take a look at the limit coming from the left and from the right. Now let's take a look at this one here. Limit of f of x as x approaches, well, it looks like we're dealing with 2 from the left, and the limit of f of x as x approaches 2 from the right. Alright, so from the left, what do we have? Things smaller than 2, so it's this one here. So it's going to be the limit of 2x squared minus 2 as x approaches 2 from the left is equal to something. And on this side here, values x approaching 2 from the right, so we're looking at values greater than 2. So x is greater than or equal to 2, so it's x plus 4. So then we'd have the limit of x plus 4 as x approaches 2 from the right. And that's equal to, well, easy polynomial function. So we're just going to plug the 2 into here, and we'll get 2 times 2 squared minus 2. That's equal to 4 times 2 is 8 minus 2 is 6. Okay? Now, on this one here, we're going to plug the 2 into here. You have 2 plus 4, and that's equal to 6. So it looks like the limit coming from the left and the limit coming from the right are the same. So, hence, this is another symbol I use. Hence, the limit of f of x as x approaches 2, just 2, because now it's approaching 2. We already figured out it's from the left and from the right, is equal to 6. Okay? So, here's another problem that a lot of people get messed up on. Now you try to do this real quick. You can press pause and see if you can do this on your own. Okay, so what we're going to do is we're going to observe what this function consists of, these subfunctions. But look, it looks like you're dealing with something less than 3, something greater than 3, and something equaling 3. Okay? So what we want to do is we want to figure out what the limit of this function is as x approaches 3. So we're interested in what's happening on the left of 3 and to the right of 3. And sometimes it seems a little counterintuitive, you know, answering this question based on the information you're given. A lot of people will think, oh, if the limit, here's the question, what is the limit of f of x as x approaches 3? And a lot of people say the answer is 2. Well, let's take a look at this a little bit closely. Without graphing this, it looks like, well, first of all, you want to answer this. Limit of f of x as x approaches 3 from the left, and the limit of f of x as x approaches 3 from the right. Okay? Now let's take a look at, because that's important to us. Remember how in the definition it says, you know, except at a itself, at that point where it says a itself, because this is the a itself right here. X equaling 3 is the a. We're interested in where are you going on the function itself, going from the left and from the right. Okay, so really memorize that and kind of understand that, because it's where you're going. Okay, it's where you're going on the function itself. All right, so let's plug in. Well, first of all, coming from the left, which one are we dealing with? Well, greater than x, that's coming from the right. Coming from the left, less than x, so it's this one here. So it's the limit of 2x plus 4 as x approaches 3 from the left. And so that's 2 times 3 plus 4. So that's 2, 6, 4, 10. Okay? And from the right, that's this one here, greater values of x are going to be, is going to be this function over here. And so x greater than 3 means values that are greater than 3. So if you're greater than 3, coming from that side going to 3, it would be this one over here. So this would be the limit of 5x minus 5 as x approaches 3 from the right. Now be really careful. Make sure you write these in here because you'll get docked off for that. So now let's plug this in. 5 times 3 minus 5. That's 5, 3, 15. 5, that's going to be 10. Okay, so these are both equal to 10, which means that the limit of the function as x approaches 3, it goes to 10. Regardless of whether or not you're given a value for this point or for the spot right on the x-axis, for the number on the x-axis equaling 3. You're interested in what's happening when you go from one side to the other and not necessarily that point. This point could very well be over here. As a matter of fact, I'm going to say this. if you have two functions, here's f of x, and here's another function, g of x, the only difference is that it has a hole in it. In that case, does the limit, and these are actually identical functions, if f of x is actually equal to g of x, but somehow g of x was constructed in such a way, or I'm not going to get into theory here because I don't want to start making more problems up, but the point is this though, you can actually have two functions be equal to each other, and one of them has a hole in it. One of them, they can be similar, okay, and one of them has a hole in it. The thing is, do the limits of both of these exist at this number as x approaches this a over here? So here, here, and this is a here, and this is a here. Well, sure, the limit does exist. As a matter of fact, it's fine, because as long as you're going in from this side and from this side, and on this side and on this side, and as long as they're both going to this number, so let's say this number was 3, and this number was 3, as x approaches a, it gets to 3, as x approaches a, it gets to 3, except this one has a hole in it, and maybe the point, even if the point was over here somewhere else, it'd still be, the limit would still exist, okay? The limit would still exist. Now, that's pretty much, I think that would be enough information for now. I would say if there's anything else that you have questions about, maybe if you go back and just rework maybe one of the problems or kind of listen to what I said, I think it'll clear things up. But for the most part, everything I went over in here pretty much covers at least 2 sections in any calculus book when it comes to the limits topic, and sometimes this is actually 1 section in some of the harder books. But for this tutorial here, which kind of went a little bit longer than I expected it to, there were 2 spots in here where I said remember. You remember this later on. The first one was the T formation. The second one was the T intersection, and the second one was about factoring. Again, those are pretty significant. I mentioned them for a reason. So anyway, I hope this tutorial was helpful, and really try to understand that you're walking on a curve. As long as you can get there from both sides, just like going to school, you can get there several different ways. The function at which you get there doesn't necessarily mean the school has to be open. Your class may be out of session. That means that the point's not there, but you still got to school. It means going either way from the left or from the right or north or south or east or west. You still get there, okay? And that's pretty much what this means. And I think this last example I did over here should really kind of make it more understandable, the intricacies of this definition. And know that just because something is defined to be maybe a point, you're really interested in this. You're always interested in, yes, but what am I really walking on? I'm walking on this path. I really don't care what's going on over here. You see, this could very well be your teacher on his way to class. But the point is, you're talking about the classroom. It doesn't matter whether there's people there or not. You're interested in going to this location. You're always interested in that right there. Anyway, just make sure you guys remember it's the path that you're on that you're interested in. And so anyway, I hope this tutorial was helpful. So good luck with your homework and tests in the future, and thank you for watching.